Hello. So, this is a continuation of the last lecture where we will talk about some more problems on finding out the natural frequency and mode shape of a bar under axial vibration, and then we will prove the orthogonality of mode shape of a bar under axial vibration. So, let us go into this example of a bar which is undergoing axial vibration, but it has a very different boundary condition where one end, that is at x equal to 0, is fixed, while at other end, that is at x equal to m, there is a concentrated mass m. So, this is a concentrated mass or a point mass, if you want to call it that way. Point mass at x equal to L, and we want to find out the natural frequencies and mode shape of this system. So, in order to do that, we have to proceed in the similar way. So, we know that the generic solution of phi x is sin C1 sin beta x and C2 cos beta x. So, this is the generic solution. Now, on this we have to impose the boundary conditions. So, let us look into what are the boundary conditions. So, the first boundary condition is at x equal to 0, my displacement is equal to 0. u0 t is equal to 0, which will give us phi 0 is equal to 0. I have skipped some of the intermediate step because this is similar to the examples what we have done earlier. So, if phi 0 is equal to 0, from this we will get that C2 is also equal to 0. Now, if C2 is equal to 0, the expression for mode shape is becoming simplified, and I have phi x is equal to C1 sin beta x. So, this is the solution. So, I have phi x as sin C1 into sin beta x. Now, I need to find out the possible solution of C1 and beta. Now, therefore, I would need the boundary condition at x equal to 0. So, let me go into the boundary condition at x equal to L. So, now let us see at x equal to L, let me draw the free body diagram. So, what is going to happen? So, this is the rod, this is the concentrated mass m. So, this concentrated mass is going to vibrate with a degree of freedom of u0 t, sorry, not u0, this is ul t. So, it is, so therefore, this see the displacement at x equal to L is u L t. Therefore, the concentrating mass m, capital M, is also undergoing a vibration with a degree of freedom of ULT. So, ULT is its degree of freedom. Therefore, an inertial force will act on the concentrated mass, which will be m into u double dot L comma t. Now, this inertial force is going to get balanced by the internal axial force acting at the x equal to L point. So, let me call the internal force to be F of L t, and similarly an equal and opposite force F L t is also acting on the rod. Now, if I write down the force balance equation of the concentrated mass, so let me write down the force balance of mass m. What are we going to get? We are going to get m u double dot L comma t plus f of L comma t is equal to 0. Now, I can replace f of L comma t as m u double dot L comma t plus E a into del u by del x at x equal to L is equal to 0. Now, under normal mode of vibration, I can write this expression, which is going to be phi L into T double dot T plus E a phi dash L into T t is equal to 0. So, what I have done? I have just written u L t as phi L into T t under normal mode. And then substituted into the previous boundary condition. So, now what I can do to this is I can write this as m into phi L into T double dot T. I divide both sides by T t, and then I have E a into phi dash L equals to 0. Now, what is this T double dot T by T t? If we go back to what we have done when we were physically explaining the meaning of a normal mode of vibration, we had seen that this ratio was minus omega square, where omega is the natural frequency of the system. So, I just write that down in the above equation, and I write this as minus omega square m phi L plus E a into phi dash L equals to 0. So, that I can write as minus omega square m C1 sin beta L plus E a beta C1 cos beta L equals to 0. So, this can actually be written as minus omega square m by E a into tan beta L plus 1 is equal to 0. So, this can actually be written as tan beta L into is equal to omega square L by omega square into tan beta L equals to, sorry for this. So, I can write this as omega square into capital M by E a into beta equals to 1. Now, if we remember, omega square is beta square, beta square is omega square into m by E a. So, omega square by E a can be written as beta square by small m. So, that is what I am going to do here, and by writing this here, I will write beta square capital M by small m into beta into tan beta L is equal to 1. So, that is going to give me beta L m by small m into L into tan beta L is equal to 1. So, that can further be simplified as beta L into tan beta L is equal to small m L by capital M, right. So, this is of the form z into tan z is equal to some constant which is m L by m. So, this expression can be solved numerically given the value of small m, capital M and L, and the solution is going to will give beta. Now, once we know beta, we can find out omega. So, once we know beta, we can find out omega and therefore, find out natural frequencies of the system. So, once we find out the natural frequencies, the mode shapes can also be found out in a similar fashion. So, this is a very good example to see how to, in a general form, we find out the natural frequency of a bar under a slightly difficult boundary condition. So, a good example is to also find out the natural frequency of a bar where there is a spring k at one of the end. So, with this, we will move into the next part of this lecture, where we will try to prove the orthogonality of mode shape. So, let us start by writing down the equation of motion under the rth normal mode. So, under rth normal mode, the equation of motion can be written as d dx E A x d phi r. So, what I have done? So, I have written the form part of the equation of motion under the rth normal mode. So, this equation we have derived earlier when we were deriving the normal mode of vibration. So, this is for the rth normal mode. Now, let us write for the sth normal mode. So, if we write for the sth normal mode, we will have d dx into E A x d phi s by dx is minus omega s square mx. This is equation 2. Now, please notice that unlike the previous case where we have assumed a rod having a uniform cross section, so that E A and m was not a function of x, but rather a constant, we have removed that assumption for this derivation. So, in this derivation we are going to derive the orthogonality for any arbitrary non-uniform distribution of E, A and x. So, we are no longer putting the constraint that the area is uniform, the Young's modulus is uniform with x and the mass distribution is uniform. So, this I am emphasizing because you will be seeing after the end of this derivation that the orthogonality of the mode shapes hold for any arbitrary condition. It is not restricted for the simple case where we have a uniform cross section or uniform distribution of the material parameter. For any non-uniform distribution, any non-uniform cross section, the orthogonality of mode shape holds. Now, let us go ahead further with the derivation. So, let us do one thing. So, we had the equation 1 which was d dx Now, I am going to pre-multiply both sides with phi s x I am pre-multiplying with phi s x and then integrating between 0 to L. Now, I am trying to evaluate this integral. So, what I do is that I integrate by part of the left hand side. So, integrating by parts, we get this as phi s x Now, let us look into this part carefully. Now, if at x equal to 0, the rod has a fixed end, then phi x goes to 0. So, if at x equal to 0, it has a free end, then this part goes equal to 0. Similarly, at x equal to L, if it is a free end, then this goes to 0. If it is a fixed end, then this goes to 0. Therefore, this entire expression goes to 0 for fixed or free condition, free boundary condition. So, this part goes to 0, therefore, this, so given any condition. So, there are two possible conditions for the boundary of a bar. One is either it is fixed or it is free. So, we have seen whether it is fixed or free, this part of the expression is going to go to 0, and therefore, this equation is going to boil down to 0 to L d phi s dx E a x d phi r dx into dx is equal to minus omega r square So, this is one expression that we get hold for. So, now let us go to the next part, where we start with the rth normal mode, that is d dx right. So, this is the equation of equation 2. So, what I do to equation 2 is I multiply with phi r x and integrate it between 0 to L. And I do the similar procedure. I again integrate this by part, and if I do this and if I apply the boundary condition, I will see that this will boil down to 0 to L d phi r dx into E A x d phi s by dx Now, what we do is that we subtract the previous expression, the previous similar expression that we have got from this expression. Now, let us look into it carefully. The LHS of this equation and the LHS of the previous equation is equal to each other. So, if we subtract the previous equation from this equation, we are just left with omega r square minus omega s square into 0 to L phi r x m x into phi s x dx is equal to 0. So, now since omega, so let me write this. So, what I am going to get is omega r square minus omega s square 0 to L phi r x m x phi s x dx, you can also put a minus if you want to, is equal to 0. So, now since r is not equal to s, omega r square is not equal to omega s square. So, if that is the case, then I am left with 0 to L phi r x m x into phi s x dx is equal to 0. And so, this is the so called orthogonality condition. So, r is not equal to s, orthogonality of mode shapes for a bar. Okay. So, this is one part. Now, if this is equal to 0, we can also say that the other expression, which was 0 to L, the expression on the LHS, which was 0 to x d phi this is the other expression that we get as a derivative of the whole proof that we have shown. So, this is also the orthogonality condition of mode shape of a bar. This is also an alternate expression of orthogonality of mode shape of a bar under longitudinal motion. So, these two expressions, once for the first, they can be used to see whether we have derived the mode shapes correctly. Second, they can also be very useful when we are doing modal analysis to find out the response of a continuous system, which is similar to the way by which we used orthogonality of mode shape in a multi-degree of freedom system to solve the equation of a multi-degree of freedom using modal analysis. The similar approach will be here used for continuous system, where these two orthogonality conditions will be used, and that will simplify the solution of a continuous system. With this, we will end this lecture. Thank you.